Okay, so here we're going to have the very last section of chapter 11, and just as a reminder, we're talking about solutions. And when we talk about solutions, if we think all the way back to our basic definitions, they are homogeneous mixtures, meaning you cannot see the individual parts and pieces, but because it's a mixture, it could technically be separated by physical means. Okay, and some of those physical means might be a little bit more invasive. For example, with brass, you would most likely have to melt that down, separate it by density, or react something out of it. Some of them are a little bit easier to separate, but it's what a solution is. It's simply a homogeneous mixture where you cannot see the parts and pieces of the mixture. Okay, so we have a couple more sections. The last thing that we're going to talk about here is osmotic pressure. Now, osmotic pressure is our third, what we refer to as colligative property. Okay, we already saw boiling point elevation, where we can raise the boiling point of a substance by adding in a second material, and also we saw freezing point depression, or we can actually lower the freezing point of something by adding in something separate. Now remember, we're not chemically reacting them, we're just adding to the mixture here. Okay, now first we got to talk about what's called a semi-permeable membrane, which you most likely heard about in biology when you talked about the cell. This is some type of partition or separation that allows solvent particles, but typically not the solute particles. It mostly has to do with the size when you're talking about the cell, but what it will do is it will separate a solution from a pure solvent. So if you see here, here's our semi-permeable membrane. Over here you have the solution that has the solute and the solvent particles. Here you have what's called the semi-permeable membrane, and what happens is that essentially a lot of times we talk about water. So if here is your original solution, water is going to run in to kind of help dilute it and help it reach equilibrium. And the difference, if this is the initial set of conditions and the final, the difference between those two levels is what we refer to as the osmotic pressure. Okay, and we've heard about the term osmosis before. Osmosis is the flow of a solvent through a semi-permeable membrane. You may have in biology heard us define diffusion is a random mixing of particles, and osmosis applies to water. Chemistry, we're just going to broaden that horizon a little bit and just say solvent, which a lot of times is water. So we're not completely changing it. Now, when the system has reached equilibrium, the water levels will be different since there is a greater hydrostatic pressure in the solution. That's a fancy word. Hydro means water, so there's a larger amount of pressure coming from the liquid that's in that solution. So if this is the original, again, the initial set of conditions, here you have time going down. What happens is that water is rushing in, and you'll notice we go from this green to kind of this lighter green color and then finally to this blue color. And the difference between the original water level, excuse me, and the final water level is what we refer to as what's again the osmotic pressure once it reaches equilibrium, which is really just how diffuse the material needs to be. Now, the osmotic pressure is also again referred to, I keep defining it in different ways, but simply the extra pressure in that solution. So another way to think about it is osmosis may be prevented by applying the pressure to a solution that's equal to the osmotic pressure. So if it wanted to rush in, woo, here it goes, okay, this would be the applied pressure needed to stop osmosis, which is pushing down this way, would have to be equal to the osmotic pressure. Okay, I think that's pretty self-evident, but just to point that out. And why do we care, right? That's always the take-home. All right, why are we doing this again? One, because they tell us we have to, but two, it's used to characterize solutions based on what the osmotic pressure of them. We also can use this to calculate molar masses. Oh, okay, here's another one. So pi, this little pi thing is what we refer to osmotic pressure. This is usually in ATMs. This is the equation that we get for osmotic pressure. M is molarity. Okay, remember it's a capital M, so it's molarity. With the freezing point and boiling point equations, we saw lowercase m, which was molality, which is not the case here. We're back to molarity, which is moles per liter, just like it always has been. R is the gas law constant. It's our regular 0.08206 liters times ATMs, moles Kelvin. T is the temperature in Kelvin. Okay, so for example, I've got 1.00 times 10 to the negative third grams of a protein is mixed with water to make 100 mils of the solution. The osmotic pressure is 1.12 torr. Now we want to find the molar mass. Now you may go, I can't, I don't know how, I'm not sure how I would do that. But if you go back to definitions here, we're going to have to figure out molar mass is going to be grams per mole. Now, they're already telling me the grams right here. Oops, I'm off a little bit. They're already telling me the grams. So my grams is going to be equal to 1.00 times 10 to the negative third. So what I have to figure out is the moles, and then I'm golden. And if you look at it, they give me the volume. I'm going to use that at the end, because if you remember way back when, we can use molarity to convert between liters to moles. Okay, so the only thing we really have to figure out, we have our volume, we just have to figure out our molarity. And they tell me the osmotic pressure, they also tell me the temperature. So there are a few curveballs I'm going to point out, but ultimately if I can figure out the molarity, I can go use molarity to go from liters to moles, and then take my grams and divide it by that amount, and there's my molar mass. So let's see this. And this is more steps in the book as always. Okay, here is write the equation first. Here's my osmotic pressure. Now, they did give me the osmotic pressure in torr. I've got to get it to ATM because I'm using the ideal gas constant. So this is just the conversion. I'm solving for molarity, and again, as always, we got to have Kelvin for our temperature value. Excuse me, so we figure out our molarity to be 6.01 times 10 to the negative fifth moles times liters of solution. Now again, another curveball, if we're going to use molarity, it is in liters, so we just had to convert from milliliters to liters. We then multiply it by the molarity to figure out the moles of the protein, and then like I mentioned, molar mass is mass divided by moles. We end up with 1.66 times 10 to the fourth grams per moles for that protein. Then you could go back and go against known compounds and figure out what you were dealing with if they gave you some options, which they didn't do. Okay, now the next thing, another example of this is dialysis. It's an artificial kidney machine that helps purify blood. Essentially, it's a little bit different in the fact that our membrane, here comes you pump the blood out of the body, here comes the impure blood. This would be our dialysis machine, and we kind of force it so that the waste products dialyze out, the purified blood goes back in, which people have to use when they have issues with their kidneys, and that's a way simple version, but you can use osmotic pressure to help with dialysis. You may have also heard of a reverse osmosis system where the pressure greater than the osmotic pressure is applied to a solution, and this is going to cause a net flow of solvent particles back this way. Okay, so we do this, so in essence we're allowing the solvent to go out and we're leaving all the junk we don't want back here. You may have a reverse osmosis filter in your house, or desalination is the same process, it requires a pretty decent amount of energy. Okay, now with colligative properties and electrolyte solutions, remember electrolytes, just as a quick review, you've got non-electrolytes, which do not have any ions. Then you've got weak, which are going to what we refer to as partially ionized, strong, which are going to completely ionize. Okay, because if you remember, colligative properties is all due to the number of particles in solution. So if you get some of these strong ionic compounds that give off multiple ions, it's going to significantly increase the number of particles per solution, which is going to increase those colligative properties, which is how we pick certain versions of rock salt. Okay, so again, as a review, it depends on the total concentration of solute particles or the number of solute particles that are dissolved, in terms of how far you can get the boiling point to elevate, how far you can get the freezing point to depress. Now we have to take into account what's called the Van Hoff factor in solutions with ions. Now the Van Hoff factor is this lowercase I, and it's a ratio simply between the moles of solution particles and moles of solute. Okay, so it's just a ratio for how many are present there. Now the number of or in other words, it's the number of particles the solute will break up to in solution, and we assume that all ions are broken up. Excuse me. Now what happens is that the observed I factor is actually smaller than expected, because what happens is even though we keep giving you these absolute versions, like as soon as, if we look at this down here and we say this is a solution of sodium chloride, we know sodium chloride is completely soluble, so in theory every one that we dump in there splits up. Well, the reality of it is that for highly charged ions, there is a small amount of what we refer to as called ion pairing. So even though we dump all of them in, a small amount of them will kind of come back together, and we take that into account. It will affect colligative properties, so that's why we have to put it in if it's given. If there's no mention of the Van Hoff factor, then you can't just generate it and create it. Or if it's not an ionic, situation where, you have to take into account. But if it's mentioned, it's the same equation, you just have to plug it in there. Okay, so again, here's your freezing point, boiling point equation. Here's your osmotic pressure. Now, just to show you what we mean, sodium chloride, we would expect to split up into sodium and chloride. So we would expect to get essentially 2.0 particles. The observed is 1.9, so it's slightly smaller. Okay, magnesium and chloride, we would expect, let's see if I can get a pen here. We would expect magnesium chloride to split up into magnesium, which has a 2 plus, as well as 2 chlorides. So that's where we get the 3 from. The observed is actually 2.7. Okay, magnesium sulfate, again, you've got 1 ion of magnesium, 1 ion of sulfate. This one has a larger difference here. Excuse me, because the expected would be 2.0, the observed is 1.3. These would have to be given to you. You wouldn't be able to just wouldn't expect you to memorize these. Iron chloride, we get a 4 because iron is going to split into, there we go, iron 3 as well as 3 chlorides. That's where the 4 comes from. Now glucose, here's our asterisk. Glucose is a molecular compound. No ions, so it's only going to be 1 particle because it's not going to split into anything. And the observed is also 1 because there's no ion pairing. So that's the non-electrolyte. That's the trick that they like to throw at you every once in a while. Okay, so osmotic pressure is just to show you, compare the Van Hoff factor observed versus expected. Okay, if we had this lovely solution of the iron, oh, this is a complex ion, which you should be covering possibly, but we'll do in this unit, and was 10.8 ATMs. Compare the Van Hoff factor observed and expected. So here is what we would have expected it to be. That simply would have come from 1 iron, 2 of our nitrogen-based ions, as well as 2 sulfates. And all you had to do was solve. They gave you everything else. You had to solve for I. I came out to be 4.4. It's just that the observed was less simply because of high ion pairing, and that's a good enough explanation. If you remember that term, you're going to be in good shape. Okay, last but not least, colloids are a special type of mixture that we've seen. They can be identified with the Tyndall effect. They usually have kind of medium-sized particles. And what happens with the Tyndall effect is if you're comparing a solution versus a suspension, okay, and a colloid is also called a colloidal dispersion. It's a suspension of tiny but visible particles in a medium. So you can see them, but they're still pretty tiny. I know, it's kind of an oxymoron here. But for the Tyndall effect, this is where we talk about fog. For a colloid, I'm guessing this first one is a solution because you can kind of see it past. But if this is a colloid, it's going to bounce back off of this red one right here. Okay, and this is why when you're in fog, you don't put your high beams on, because if you have the high beams, they hit the fog, well, they come right back up and they hit you in the face, which is not good. But if you keep your low beams on, then they're not going to bounce back and hit you. Anyway, probably a bad picture, and I probably have the angle of reflection wrong, but close enough, you get the point. These are some other types of colloids, milk, whipped cream. It kind of gives all the different dispersion methods in that respect. Okay, there you go. I hope that